welcome to this very special open lecture. I'm going to introduce myself very quickly. My name is Eric Bahar. I am the Dean of the Faculty of Business at Berlin International University of Applied Sciences, and we're very happy to host this open lecture with Professor Dr. Florian Artinger. So what I will do before my colleague starts the open lecture is to provide you with some background information about our speaker this evening. So Professor Artinger is a professor for digital business at Berlin International University of Applied Sciences. He is currently the head of program of our digital business program. Florian is the co-founder and managing partner of Simply Rational, the Decision Institute, and he's also an associated scientist at the Max Planck Institute for Human Development. Florian received his PhD in behavioral economics from the Max Planck Institute and has been working as a researcher at the University of Warwick, the University of Oxford, the University of Chicago as well. His work has been published in leading international journals and has received also a number of awards. He is a frequent keynote speaker at practitioner conferences and has taught managers and financial analysts the arts and science of good decision making. And Florian, it's an honor to have you in this open lecture, which is called, as you all know, from the image that we sent to everybody in the community, Augmented Intelligence, combining human and machine intelligence. So Florian, I would say the floor is all yours. Thank you very much for this very, very interesting talk. And so I will mute my mic now. Go ahead.
Eric, thank you very much for the kind introduction. That's really lovely for those words. Yes, and I'll take it away straight away. Yes, so as Eric already suggested, the title of the talk today is Augmented Intelligence, combining human and machine intelligence. Now, let me go back to the year 2001, where actually a quiet revolution took place in Seattle. Back then in 2001, Amazon was already one of the rising stars on the internet horizon. And quickly growing when selling books actually. And the crown jewels of Amazon were actually its critics. So it had a very large number of book critics that were sitting in the headquarters in Seattle. And they were so widely recognized that even the New York Times or the Washington Post were referring to them basically. And they had a very prominent place on the landing page of Amazon. Now in 2001, something quite dramatic happened. Amazon started experimenting what's often been referred to as artificial intelligence, or what I'll be kind of more specifically be calling machine learning, basically, or machine intelligence. That is, Amazon was sitting on this vast amount of data from its clients, and was seeing whether kind of recommendations could be produced on an individual basis for its clients. And it very quickly emerged that these recommendations based on the artificial intelligence machine learning were vastly better than what any of the book critics actually could achieve, particularly in terms of looking at the revenues that it generated. Now, what this recommendation engine was basically was a very complex algorithm that even the data scientists that were designing this algorithm didn't really know how it worked. They only knew, okay, a certain amount of information went in there, and then certain recommendations came out there. But how exactly kind of these things work is not transparent even to those people that constructed this very algorithm in the first place. Now, many tech companies, politicians, and scientists since then have come to believe two things. First of all, the best decisions require complex black box algorithms, and human judgment can ever only be second best, such as those Amazon critics. And this has, in the last 20 years, really strongly shaped our world, regardless where we are dialing into this call, whether you're coming from Colombia, for instance, or whether you're coming in from Thailand, or whether you are sitting currently in Russia. These algorithms have become really a strong driving force. Now, what I'd like to do in this coming talk is actually to challenge those two assumptions and to walk you through why these assumptions might actually not hold anymore. Now, the first assumption is the best decisions require complex black box algorithms. Now, what we are currently working on, also we've been doing research at the Max Planck Institute, but also as the company and at Berlin International, we're working on something called augmented intelligence. So augmented intelligence is the idea that you combine actually human machine intelligence in order kind of to achieve a superior outcome. Now, how do you do that exactly? As you've seen with the Amazon example, so experts seem to have some very specific knowledge that can be highly valued in the first place. Now, coming from cognitive science psychology, one can actually formalize such a knowledge basically and put it into a type of a mini algorithm, which are usually very simple rules actually, but which are highly effective. And this can be integrated with the complex algorithms that usually emerge from machine learning, and to generally those combined produce in very simple and easy to understand decision rules that can be interpreted by anyone basically. And we suggest this is one way forward, the next step in the development of machine learning, coming back into the world with the human being and together making decisions. Now, what does that exactly mean? This might sound awfully abstract in the first place. Let me dive into some examples. The first one is bail decisions of judges, and the second one is actually decisions that you make in the hospital after you've had an operation. Now let's first go to the bail decisions of judges. Now the prediction is that the defendant appear in court without bail. Now in the United States, judges make the decision when a defendant appears before them whether or not they let them free again, either with or without bail. Now, an important element in this consideration is that people who are coming from a weaker social background, that is having a lower income, for instance, are likely to not be able to pay the bail in the first place, whereas others who are richer in the first place might have less of a difficulty here. So the judge really needs to kind of balance here his judgment in order not kind of to be discriminating against people from a poorer background. So this is a very important decision indeed to make. Now, what colleagues of us from the Max Planck Institute, from Stanford University, and from Microsoft Research did, they ran a black box machine learning algorithms, as so often done nowadays, on a whole range of information that is available in this context. So there's a lot of data. Makes use of many different types of variables, such as the type of offense we are actually looking at, whether a weapon was used, the age of the defendant, etc. It's 64 different variables that are actually introduced in this black box machine learning algorithm. Now, what they did then afterwards, they examined all of this information critically, and together with experts, zoomed in onto 2 specific variables only. So those are 64, they only used 2, and that is age and the past court dates missed. Now, how does it exactly work? So assume a person is between, let's say, 35 years old. In the first row here, would be getting a score of 2, and has had 1 past court dates missed, would be getting a score of 6 here. You simply add up those 2 scores, 2 and 6, which gets you to a flight risk of 8. Now, if the sum of those 2 variables, so age and past court dates missed, is smaller than 10, then this augmented intelligence, this very simple algorithm, this transparent algorithm, makes a prediction that the defendant will appear in court without bail. Now, this seems almost ludicrous, right? I mean, how can something that is so simple perform just close to what a complex machinery is able to achieve in the first place, the black box machine learning algorithm that they're using. Now, let me show you the results. Now, as I said, it's desirable to avoid using bail in as many cases as possible. Now, first of all, you see here the judgment of experienced judges. These judges had at least 1,000 cases previously in which they were examining whether or not a defendant should be subject to bail. Now, what they did basically is 69% of all of those defendants they were looking at, they were letting free without bail. 31% had to pay bail. Now, of those 69%, 13% of the defendants without bail failed actually to appear in court. So the error rate, so to speak, is 13% out of 69%. Now, how do the algorithms do? Now, the black box machine learning algorithm used here is, by these standards, vastly better than the experienced judges, similar to the case you would have seen at Amazon. So the black box machine learning algorithm sets 79% of defendants free. So 10 percentage points more than the experienced judges, which is in the interest also of the lawmaker in this case, but only has an error rate of 12.4 percentage points. So a similar error rate, but vastly many more people are set free actually by that algorithm. Makes, in comparison, relatively fewer mistakes than the experienced judges. Now, let us examine the results for the augmented intelligence that we are looking at. It only uses 2 of the variables of the black box machine learning algorithm. Now, what you see here is that the augmented intelligence basically achieves the very same performance than the black box machine learning algorithm. That is, 79% of the defendants are set free without any bail, and 13% fail to appear in court. So the error rate here is 13%. So despite being so radically more simple, despite being so transparent, the performance of this augmented intelligence algorithm is as good as the black box machine learning algorithm. And this is quite a challenge to the conventional wisdom, the conventional understanding that you really must have complex algorithms that make use of all the data and that perfectly intransparent, because this intransparency also comes at an incredible cost, right? Somebody who would like to question whether or not they are have to pay bail. This coming from a machine learning algorithm, it is not clear why the algorithm decided, right? In a law context, this might be really, really difficult if people don't understand why certain things happen. But this is actually even more extreme in our next case when we are moving on to the medical domain. Now, here the prediction is, does a patient die after an operation? Now, this is joint work of Niklas Keller, one of the co-founders of Simply Russian, and also from the Max Planck Institute, together with the Charité University Hospital here in Berlin. These are the following numbers they started out with. So they were having a look at patients who die after an operation. Now, 27% of these patients that die after an operation are in intensive care unit, whereas 73% of those patients are in a normal care unit, not in an intensive care unit. That is, potentially there are many, many patients that would have considerably profited from being allocated to the intensive care unit, but which were not, and as a result, potentially died actually. So there is a really grave misallocation potentially here. And the question is, how can you address this problem? Now, again, as in the law context before, this is a very complex problem with many, many dozens of variables that potentially affect whether or not one should send one to the intensive care unit, or rather kind of leave them in the normal care unit. What you see over here is just a snapshot of the tools that are used. And yes, they don't only seem complex, they are very complex indeed in their use. So one must be quite experienced actually, and the complexity itself even invites that experienced doctors make mistakes with these tools. So the question is, can we tackle that? Can we really radically improve upon kind of the current standards? That is really kind of make these things transparent and simple. Now, what Niklas and colleagues did together with experts in this domain, they constructed a very simple decision tree. And here you see the simple decision tree, our augmented intelligence. First of all, they looked at, okay, were there any comorbidities? So were there any other severe illnesses that the patient would have? If yes, then this would immediately imply, yes, please go to the intensive care unit. And if no, then they would come to the second variable. And this variable actually is the expert itself. Now, what's the intuition of the physician? how does he really feel about the situation? Does his gut feeling actually tell him to rather kind of give that patient to the intensive care? If yes, then please do so, because this really is a very important variable in this given context, maybe surprisingly, at least kind of by the standards that Amazon set, kind of to leave everything to the machine. And lastly, so if the physician's intuition was no, actually, I don't think this patient should be at intensive care, we're looking at cardiac surgery. So any kind of heart surgery. Did the patient actually in the past have some cardiac surgery? If this was the case, then indeed one should give this patient to intensive care. Under any other circumstances, under any other of the many information that are available there, the patient should be allocated to the normal station. So this is radically simple. It's something called where you actually can put the machine learning as a laminated pocket card into your pocket, basically, and gives this to doctors such that they have it available at any one moment, irrespective of their technological environment, basically. Now, how does this radically simple solution perform against the conventional complex standards? Now, that's what you see here. So on the left-hand side, you've got the prediction accuracy. Does patient die after the operation? The augmented intelligence algorithm identifies 91% correctly with this very simple decision tree, whether or not a patient should die and whether they should be allocated to intensive care unit, basically. Now you achieve the same thing with the CC score, card classification and regression trees, for those coming from a data science background, on ASA score. Now the CC score and ASA score, they are tools that are kind of classically used in this context, but which are not transparent. They're highly complex, and doctors can't make an assessment why this machinery now kind of suddenly decides whether or not someone should be admitted to the intensive care unit. By contrast, it's very transparent with regards to the augmented intelligence. They can question whether or not actually maybe the patient isn't kind of the average patient that really kind of adheres to this pattern, or maybe this patient is an outlier, is rather kind of different from the average and should be therefore rather treated differently. Therefore, this combination of actually having kind of the systematic structure that the simple decision tree allows, plus then the expert knowledge actually usually also implies that those two things, the simple decision tree plus the expert knowledge, that they jointly can perform even better. Now, having questioned this very assumption that complex problems require complex solutions, and these are only two examples, I could give you a number more, I'd like to turn to the second assumption that academics, people from the tech industry, but also politicians have made. Human judgment can ever only be second best in comparison to those machine learning algorithms. Now, let me have a look at the domain of investment in this case. Now, dividing one's money between different investment options. So assume you have inherited from your granny 100,000 euros. How would you distribute this 100,000 euros between different options? Say you've got 10 different stocks. You were looking at, they seem to you very appealing. How do you distribute this 100,000 euros between these 10 different stocks? You might think kind of maybe investing in the first stock where 20,000 euros might be a good idea, whereas in the second stock, you might be going by 5,000 euros and so on and so forth, until you've divided all your money up, basically. Now, somebody who received the Nobel Prize for solving and addressing this problem is Harry Markowitz. So Harry Markowitz in 1952 discovered or developed the mean variance model, which tells you exactly and optimally how to divide your money among a number of assets, basically. Now notice that this is an environment with a vast amount of data. Historically, the financial markets have been driven by data, basically. I mean, this is kind of far beyond the age of data science in the first place. So this is a very similar context also kind of to the one that Amazon is in, but actually kind of predated the Amazon context. Now, the question is really that Harry Markowitz was put after he won the Nobel Prize for his mean variance model. So Professor Markowitz, he was asked in an interview, how did you do your investment yourself? The interviewer obviously expecting that Harry Markowitz kind of would say, well, I used my model and did maybe kind of following modern variant of that model, because the number of modern variants around. To the surprise of the interview, Harry Markowitz said, no, I didn't use my model, but I used what's now called the 1/n heuristic. So again, another very simple decision strategy. Now, what is 1/n? Assume you have 100,000 euros. N refers to the number of assets that I have. So 10 stocks, for instance. So 1 divided by n means that I divide my 100,000 euros. So 1 divided by n means that each stock gets 10% basically of these 100,000 euros in the first place. So nothing kind of I weigh those combinations differently, but each stock gets 10,000 euros regardless what's happening essentially. Now not only the journalist was very surprised by Markowitz's answer, but he was actually rather kind of critically received upon in the academic community. And many kind of even ridiculed Markowitz's decision. How could somebody who is an expert in it and mathematically proved what's correct, how could somebody such as him only make such a foolish decision? Now, again, colleagues of ours from the London Business School actually tested Markowitz's intuition, right? He did not follow his mathematical proof, but he had an intuition how to do it. They wanted to see, okay, how bad is actually his intuition in terms of performance in comparison to the actual mean variance model. And so first of all, what you see here is for 6 different portfolios. So in a portfolio, you have different, for instance, stocks, and there you have to divide your money across these stocks, basically. They took those 6 portfolios and tested how the mean variance performed in terms of hindsight. So only looking at the past, basically, and seeing, okay, if I do mean variance in terms of, okay, I do as the model suggests today, and then observe in a year what the performance is. And you already see here a dramatic difference. That is, the performance, the return, or the Sharpe ratio, to be more specific, dramatically drops in prediction as opposed to only looking at historic data. Due to the uncertainties, the unforeseeability that you do have when you're actually facing the future as opposed to only dealing with the past, where you know everything. Now, how does the 1/n model heuristic perform in comparison? Also looking at the future, because that's really only what is relevant, right? The past isn't relevant, but it must perform well given an uncertain future. And that's the performance of the heuristic. So for every and each of these portfolios, the heuristic did at least as well as the mean variance model, or indeed 14 modern variants of the mean variance model. That is indeed, Markowitz's prediction was spot on. Markowitz's intuition was spot on when he relied on his intuition as opposed to going with his mathematical proofs that earned him the Nobel Prize. Now, let me go back and give you a second example with regards to human intuition. Let me go back to an environment that is very similar to the Amazon environment. Now we're looking at Vuga here. Vuga is a Berlin-based company that is developing games, more precisely games for the smartphone. And they have a freemium model where they basically invite people to attend for a certain time for free, and then people must make a certain kind of purchases in game, and that's how they make their money. And obviously here at stake is what are the types of marketing measures that you have, and the more you expect to earn from a given customer, basically, the more you might want to invest in marketing measures. Therefore, kind of the important prediction you make in this context, how much money will a customer spend within a year? So again, it's a lot of data, basically. It's an online context, just as Amazon, and it's a product. Here's Jelly Splash, which is the game, one of the many games they're having, basically. And you need to make, again, a prediction about a customer, essentially. So it's a very similar setup in the context to which Amazon actually dismissed their expert team of book reviewers. Now, one of the heads of the data science and marketing department basically challenged the data science team and suggested to them, okay, please try to outsmart my prediction. My prediction is that the revenue in the first 7 days where a customer actually needs to pay, you simply take ×6 in order to predict the revenues 360 days later. So only take one variable, the revenue in the first 7 days, take it ×6, and that's my prediction. I give you all of the data that we have basically, and please do try to beat my model. Again, the marketing manager's intuition here, the very simple heuristics, such as the ones that we have seen now in the 3 previous examples. These are the results. So it's error again, so kind of the lower the better. And what you see here, we see here 4 different models that are conventional models in machine learning, a logistic regression, L1 regularization, random forest, and the now very popular extreme gradient boosting. And you see here in comparison to this multiplier heuristic, so simply kind of take the last 7 days of revenue ×6, respectively, where the machine estimates this multiplier, there is no difference at all. So just adding lots of data in this context, again, does not make any difference. Now, how is this possible, kind of given that Amazon did so very well without its experts in the first place? Now, what we did is, apart from this collaboration with Vuga here, we also had a look at 15 further data sets and looked at the multiplier heuristic and 15 other contexts. And what we find here is even more striking results, that the multiplier heuristics actually, under some situations, in some contexts, can systematically outperform the complex algorithms. Now, what is the driving, what creates such differences, such stark differences between what is commonly believed should be the case, i.e. that human judgment is only second best and you always need complex black box algorithms? I mean, am I presenting kind of some sorts of magic? Well, not at all, actually. But I mean, the magic here lies really in knowing precisely when to use black box machine learning, when to rely on human intuition, respectively, when actually to combine both via transparent and very simple models, basically. No, that's precisely what we show in our research here. So when to rely on human and when on algorithms. So machine learning algorithms can only perform well if 3 conditions hold. The environment must not change. So think back at Amazon. Think back of its core business in 2001, which were books. The demand for books, there isn't much dynamics basically in this context at all. But this kind of demand for books that's very stable, very constant. Whereas in the Vuga example, but also in the example by Markowitz, it's a highly volatile environment. So given these highly volatile environments, these are actually usually not conditions under which machine learning algorithms can outperform human judgment. And actually, the more volatile the context, the less well such machine learning algorithms perform, because they heavily rely on historic data. Second, it really must be big data. So having not this vast amount of data available that Amazon has, but also Vuga has basically, but having less than big data. And there are many decision environments nowadays where big data is not obtainable. This also speaks critically against using machine learning. And the third element that we discover is that the time to prediction must be relatively small for the machine learning algorithm. Again, think about the Vuga example, the online games, the mobile app games, excuse me, that the prediction was 360 days in the future. Whereas for Amazon only predicted, well, the next time somebody was logging in, and ideally that person would be logging in within the next month or so, right? So the prediction horizon, again, is much shorter. And if all of these 3 things are fulfilled, indeed, Amazon's decision is perfect. And in any other context that fulfills these 3 criterion, one really should go with black box, complex machine learning algorithms. However, if that is not fulfilled, human expertise can be expected to perform as well or even better than the algorithm. And lastly, actually combining human and machine intelligence can achieve a better performance than human and machine intelligence alone. because humans usually kind of can see other aspects that the algorithm cannot see. They can identify whether a patient, for instance, is prototypical for what the algorithm really knows, or whether a patient is affected by something very, very different that is not very typical usually. So just kind of to recapture what we've been going through, and then I'm looking very much forward to all of your questions. So many tech companies, politicians, and scientists believe the best decision require complex black box algorithms. I believe and hope I've been able to show you, at least with regards to 2 cases, and as suggested, there are many other cases out there that we're currently working on, or colleagues working on indeed, that simplicity, simple algorithms, very often can be just as powerful as these black box algorithms. And what they allow in many different contexts, where it's also critical that one really kind of gets to know why a decision is made, such as in the legal context, in the medical context, but also if you think about obtaining a credit, for instance, from a bank, they allow you this transparency and really kind of assessing why something happens. Secondly, the suggestion is human judgment is ever only second best in comparison to these algorithms. And yet again, we have seen with regards to Harry Markowitz's example, as well as Jelly Splash, so Vuga, that indeed intuition can be a very powerful source for good judgment. And combining human judgment and machines, keeping them both what's called in the loop, basically, promises to actually achieve much higher and better decisions than if one kind of keeps those separate. Thank you very much for your attention, and I'm looking forward to the questions.
All right, thank you very much, Florian. So we see with digital applauses there. Thank you so much. There's a comment from Techmina from the MBA. Says that it was very informative and insightful, easy to understand the way the professor was presenting. Thank you very much. So thank you. All right, so now what we're gonna do is that you can send your questions via the chat, or you can also speak. If you want to interact with the Professor Artinger and ask a question, you're free to do so. So we're gonna go with the principle of first come, first served. And if nobody begins, I do have a question specifically precisely because of your conclusion. Let me check if there's another question before mine. You can just raise your hand, or you can just let me know also using the chat. Concerning this last part of the summary about human judgment and what you were telling us, since basically you have included some, let's say, references to behavioral economics in terms of the heuristics and so on. When we talk about human judgment, and we know that we are prone to making mistakes as well, when we're filling out forms, we're not looking at the packaging exactly, at the grams of a product that we probably think is a lot cheaper, but then it's not really cheaper because it's a lot smaller, but we think it's bigger and so on. How do you think we can mix this into let's say into a policy solution, so people can make better decisions, already knowing that human judgment is of course good, but that it also needs a little bit of a nudge or a support, because human judgment is not just one thing, right? I mean, we can have a lot of different humans with a lot of different ways of approaching problems. So how do you see this from the policy side in terms of designing better policies for consumers, for people who make mistakes?
Thank you very much for the question, Eric. Now, the assessment human judgment can ever only be second best is precisely coming from rich literature in psychology, specifically going back to Kahneman, Danny Kahneman, and Amos Tversky, Kahneman winning the Nobel Prize for his work in 2002 for that. Tversky had already died by that time. And what they find indeed is that people exhibit a number of serious biases and are anything else but rational in the first place, and rather kind of should be supported, guided by the state, which is then often referred to as nudges. So where kind of the state creates an environment that is ideally nudging people in the right direction without them actually knowing that this is a good thing in the first place. Now, how can this be that there is such a literature on people being so very bad versus actually that people can be very, very smart decision makers. Now, I think kind of a crucial decision here is that one mustn't assume that people are inherently stupid or bad per se. Rather, and I think this is also a great thing working at an academic institution, an institution that actually kind of teaches, right? If people have the possibility to learn, then they can indeed make very good decisions in the first place. If they have the right learning environment, getting good feedback, basically, then they even under some circumstances can outsmart algorithms. That being said, also machine learning algorithms have been shown to exhibit severe biases and performing badly if they are fed with bad information. So it's simply kind of a matter of kind of if you feed in something bad information into a system in the first place, of course the outcome is bad. If you don't allow people kind of to actually understand the basic mechanisms in the first place, yes, of course, they're making kind of bad decisions, and they will continue to make bad decisions. So going over to this policy context, what it basically means is, so if you follow a pure nudge approach, where you do not educate people, but where you simply kind of change the decision environment and hope that this decision environment kind of brings forth better decisions, basically. This means that you kind of leave people in the dark and they never ever will be able kind of to make good decisions. So instead of simply kind of changing decision environment, and also like some decision environments might be constructed by benevolent agents, such as hopefully the government. Other decision environments might be constructed by not so benevolent agents, right? Think about marketing campaigns by companies. I mean, they surely haven't the interest of the public in mind, but rather their own profits, basically, right? And therefore kind of might nudge people in a direction that is actually not in the best interest of the people in the first place. So what could you do? So instead of simply kind of saying, well, nudging is kind of the best way forward, it's rather kind of how can you really kind of make sure that people make good and informed decisions and that they actually learn something which they also can apply to a different new context.
On the information and how they learn. So we're not too far away from the algorithms in the sense that if we are fed with bad information and like bad education, we end up making bad decisions and through our emotions and so.
Exactly.
Okay, I think it's a very, very amazing insight. We have a question, Florian, from Eva Maria. Thank you very much for your answer. I think you could have a very long discussion on that, on the thing that you were mentioning, which is very interesting. Eva Maria, go ahead.
Hi, Florian. I'm sorry I can't put on my camera for some reason. It's not working today. Thank you so much for this really very insightful presentation. Was very great to hear. It's not really a question, but maybe you have an idea about it. I recently read a book about the man who solved the market. This is a fund in the United States who is not so popular, but they made the highest records any fund has ever made. So they beat the market by 70% every year, no matter if it went up or if it went down. And from what I grabbed from, or from what I understood from the book, is that they used algorithms they developed with big data, and that they did pretty short trades. So this fits with your one argument that it should be big, the two arguments, it should be big trader and it should be a short time horizon. But the third one, I'm not pretty sure, because you only tend to make money in the market if the market is moving. So if it's volatile. And I agree, it's maybe less volatile over a day in general. It's not a big move than over a longer time horizon, but still it needs volatility, it needs change. I'm not really expecting an answer, but maybe you have an idea how this may fit together with your results, because I found it really interesting what you were saying.
Right. So maybe regarding volatility, of course, I mean, having a certain amount of change algorithms can cope with, but they're very, very brittle. That is, just going a little bit beyond this kind of critical point, basically, of this little change that is possible, kind of they break down and make fairly bad decisions. Let me give you another example here. So there's a COVID crisis starting in spring of last year, or precisely in February. Now, many of the airplane companies that are selling their tickets online have been relying on machine learning algorithms to calculate the best prices they can offer for their tickets. And what you basically observe here, so there's a radical change in the market because of Corona. In March, these prices for flight tickets just went berserk. They were just all over the place, because because the algorithms, well, didn't know kind of what to I mean, they were not confronted with a totally novel situation, basically, and therefore weren't able to adapt at all. That is kind of, for your example also, I guess, kind of given kind of not too much of a change, this is indeed possible. Now, kind of almost kind of giving back the question, I would think kind of, I mean, usually one would expect that no one is able to beat the market consistently. If one kind of believes in the efficient market in the first place, right? Or in the efficiency of market in the first place. I wonder how that fund, after they reveal kind of how they perform, is doing now. I mean, maybe actually kind of writing that book was already kind of after they discovered that they're not performing anymore so very well, and actually are now looking into a different source of revenue, and that is selling kind of their old wisdom that is actually already kind of past their expiry date.
Well, no, it's a biography about the fund founder. It's the fund Renaissance, and it performed consistently, like Warren Buffett performed consistently with 20% over decades. So, I mean, there's an entire movement that the efficiency of markets is an ideal, which is not the reality. But what I find interesting is what you were saying, the change shouldn't be too big. And I remember in the book, it said when the market really crashed, they also had problems. So it seems to fit that some of the change seems to be okay, but not too much.
Okay.
So there were instances when they were telling that they stopped trading. I don't know if they fixed this problem one day. It's not mentioned in the book, and it's all very secret. But the fund is still there and is still running. It's closed for additional people, unfortunately. But yeah, it works. Obviously, it worked. Yeah.
Okay.
They are super rich, those people, and very famous that they made it. Now very famous since the book. Before that, they avoided publicity.
Sure.
Unlike Warren Buffett, who does the contrary.
You're referring to Renaissance, right? From Simmons, from Jim Simmons?
Yeah, exactly.
Okay, because just one short comment about that because those are the famous quants, right? And that they kind of like pick up on those imperfections, but at the same time, the interesting thing is whether they actually force the market crash after a while, which is another discussion that we are surely going to have in the future. So we have more questions. Florian, thank you, Eva Maria, for your question. We now have David's question. So David Wolny, yes, go right ahead.
Yeah, thank you very much for this very interesting and clear talk. My question pertains actually to how to put this in practice, and maybe going back to the two examples that you gave in the beginning. So when to put people on bail or when to put somebody on an ICU. How do you come up with these very simple algorithms then, or decision strategies, and or like more specifically, how do you decide when somebody's or a human's intuition is actually ecologically valid? Is it just that you take people from the field and then have been exposed to information that is relevant in that situation, or how do you come up with these very simple to understand rules?
Yes, no, thank you very much, David. No, indeed, the first and primary prerequisite is expertise. And that's also kind of like the difference to Eric's question, right? People can make lots of errors and mistakes if they have little expertise, make bad judgments. So the question is kind of a given context, okay, can we first of all identify people that have really lots of expertise? And then we have a certain kind of structured interview process that allows us kind of to guide us through what types of information do they consider, how do they combine these types of information, and that we kind of then integrate it back into kind of our knowledge of cognitive science. So what types of decision strategies are generally kind of known kind of to exist and perform well, kind of given certain certain circumstances. But then secondly, and most importantly also, I mean, the question is, okay, did these experts really have a good learning environment? Did they kind of get sufficient feedback, or the kind of positive and negative outcomes, etc.? And that's then also when we check with the algorithm. So what exactly what's the information that the algorithms rely on? And there are certain tools nowadays where you can make extreme gradient boosting, random forests, etc., to a certain degree a little bit more transparent. I mean, they're still very, very complex, basically, but you can have like a ranking, for instance, which variable kind of is more important in terms of contributing to the prediction, basically. And then we see kind of whether there is some sorts of correspondence between the expert's judgment. And often we will be kind of going back with this information to the expert and discussing with him or her how the findings from the algorithm kind of fit with their expertise. And from that, it's basically a back and forth process with us also kind of examining the data again. We kind of distill kind of this very simple decision strategy and see how well basically it performs in the end of the day. But it's the back and forth between machine and human. Human with a lot of expertise is essential, really, to guide us kind of to the right decision strategy.
Okay, so that means that you still use, even if you don't use these very complex models or algorithms in the end to make a decision, you use them to kind of deduce what the most efficient or simple heuristic could be.
Exactly, and they also serve as a benchmark, right? So how well can one perform in such a context? Very often we achieve kind of similar performance, sometimes even a better performance, but then we really know, okay, this is not just kind of our, well, here we go, we think this works, but actually a proof of concept.
All right, thank you very much.
Thank you, David.
Great, thank you, David. So there is a question, a comment from Tegmina. Tegmina, would you like to read it yourself, or would you like, because I can also read it. Okay, so I will read it then. So Tegmina says, recently I was listening to an interview with Rita J. King, a futurist and scientist at NASA. She stated confidently that in the coming decades, machines will be 10 times smarter than humans. It sounds strange, so I would just need your comments in this regard, and to what extent you think it's likely to happen.
So that's a good point. Thank you very much. So what does smarter mean? So in terms of computational power, that has long ago happened, right? So for instance, look at chess. Like expert chess players can evaluate, I think, kind of 5, 6, or 7 different moves per second, basically. Whereas if you go to Deep Blue, Deep Blue was a program developed by IBM. And actually was able, the first time was able to beat the reigning champion in world champion chess in 1996, Garry Kasparov. Now Deep Blue was already able kind of to make more than, I think, 6 million computations per second. So there's a vast difference in terms of the computational power. But what it seems here is that it's not in terms of simply kind of computational power. We are long past that stage really here, but it's more in terms of pattern detection, pattern recognition, where humans really excel. I mean, you might have come across those funny pictures where you're trying to log in and then ask kind of to identify a traffic light, something like that. I mean, how simple is that? There can't be any simpler task, right? I mean, surely those machine learning algorithms must be able kind of to easily solve that. So it's working with visual algorithms. Now, however, that's actually a serious challenge. And generally, what is believed today is that algorithms roughly kind of have the same stage as a 3- or 4-year-old in terms of kind of their judgment. And more generally, actually, there is, as of yet, these algorithms, there is no kind of general artificial intelligence. They're always only designed for very, very specific purposes. So kind of going back to Deep Blue, the chess algorithm can't cook you or can't identify pictures, or it can't work with language, or it can't. These are very, very specific. Therefore, kind of this assessment, it's computers will be 10 times better than humans. That's a nonsensical statement, I think, in and of itself. One must look at the specific task, and yes, in some tasks, as we see here, given a static environment, given lots of data, computers will be much better. But in many tasks, this is not the case, and is likely to never be the case.
Okay, so it means like it's conditional, right? Depends upon the task, and as you stated very well, like, you know, depends upon the definition, what considered to be smarter. So yeah. Thank you so much, Professor. Thank you so much.
Thank you, Jimina. Thank you, Florian. All right, do we have any other questions or any comments that you'd like to state? All right, if there are no more questions, I would say thank you very much.
Can
Florian,
I ask a quick question?
Ah, there's another question. Yes.
Yeah, sorry.
Go
I was trying to formulate my question, but actually David did a very good job of asking what I had in mind. But I think maybe just sort of in the end, it's my understanding that these kind of deep learning systems are quite vast and expensive to create and run and consume a lot of power. And maybe is the intent of augmented intelligence to kind of extract a little bit more from what this very powerful machine or creation can do. So, you know, coming up with sort of designing algorithms with specialists, sort of human intelligence to kind of come up with more practical problem-solving solutions.
Right, thank you, Boaz, for the question. So this kind of gets back to Eric's initial question. When you see, for instance, the example of the bail decisions of those judges, you see that those judges, even though they were experts, basically, they weren't very good, actually. So kind of one of the kind of postulates that I suggested to you guys, expertise kind of is the very kind of important thing. It's not completely true, because humans and also in this case judges, there are quite a number of studies, are very strongly influenced, unfortunately also, whether they just have had lunch or whether kind of they just started the day, in terms of how accurate and how well kind of they perform in their decisions, basically, right? So what we are trying to do is kind of not kind of push the boundaries kind of on all the complexities, because I think kind of many people are working on that, and there are certainly many domains where that's kind of valuable and where one kind of doesn't need even a human involved. But there are many domains where I think it's also very important that humans should and must be involved in the first place, such as the context of the law or in medicine, basically. And our simple models basically allow humans, and they might vary in their judgments because of if they have had a coffee or not, or lunch just not. They provide much more kind of a systematic way to assess the situation, and therefore might make people kind of much less liable kind of to the kind of changes in their well-being, basically. And above and beyond that, what I would like to stress is that people can see other things that have been called in the data science literature broken legs, so stuff that is not in the data, but just has happened to a person, such as this person does have a broken leg, which is atypical of what is fed into the data. And therefore they can actually, together with this very simple algorithm, where they see whether or not this broken leg makes a difference or not, they can then actually kind of make a much better decisions, really kind of using their own expertise, using their own intuition, but using also the consistency of the decision tool that we provide and develop together with the experts in combination with the algorithms.
Great,
does that address?
Yes,
okay, thank you.
It seems that just kind of normalizing or sort of expanding on the relationship between these very complex algorithms and just human intelligence seems just very important for the future. So thank you very much for your answer and your explanation.
Thank you, Boaz.
All right, thank you, Boaz, and thank you, Florian. We have another question from Thomas. So I'm going to read it, or Thomas, would you like to speak directly? Okay, so I'm going to read it. So as we know, intuition plays a crucial role in the decision-making process of a decision maker in a particular firm. But could you explain how and what factors influence the solely or partly intuitive decisions that the decision maker makes.
Thank you very much.
Yes. Okay. All right. You got it. It's in the chat also. Okay. I'm just, trying to.
Yeah. Actually, I don't see the chat, so it's wonderful that you read it out, Eric. Thank you.
Yeah.
Right. So indeed, so like there are a number of influences within organizations that might either help people to make really good decisions or actually lead to pretty bad decisions. And one thing that I'm also quite interested in is something called, in colloquial terms, so colloquially also among managers, cover your ass. So what does that mean? So particularly in management, people are often exposed to certain risks. Now, cover your ass means basically, okay, given a risky situation, such as about a new innovation that would kind of bring the company forward, I really kind of take that risk, or alternatively kind of try to avoid that risk and rather opt for a second best solution, that is an innovation that is a much smaller step forward and much less beneficial for the company, but where I know that if something goes wrong, has far less consequences for me personally, basically. That's kind of a classic example for cover your ass, essentially, kind of people trying to avoid kind of really risky decisions that would be in the interest of the company. And we find kind of that, unfortunately, kind of cover your ass is kind of quite widespread. I mean, it's even listed kind of in the Oxford English Dictionary of Idioms. Now, however, there are solutions actually to that. So that is that one has, so Amy Edmonds from Harvard has developed a really interesting approach called psychological safety. So where you empower the team such that each individual in the team realizes that actually risk-taking is very important and that failure is simply kind of part of the process. If you take risks, you cannot by definition guarantee the success. If you guarantee something, then you're not anymore in a situation of risk, but then you are in a situation of certainty. So risk always entails the possibility of failure. So if you have a team climate and if the team acknowledges that, basically, that risk-taking doesn't mean that you're always kind of the one who is successful, this already kind of brings you a great step forward. And that also, in this context, a very important role is that of leadership. So if leaders, team leaders, but also leaders in organizations exhibit behavior such that they don't cover their ass, excessively document or kind of takes the second best options and avoid these risks, basically. That also strongly influences how individuals in the organization kind of will make decisions. And taking risk also often implies that one cannot kind of assess all the consequences, but that intuition is a very important part, basically. So if an organizational climate is such that one encourages cover your ass behavior in the first place, then usually people will be shying away from using their intuition, even though this can, particularly of experts, be a very valuable source for good judgment, especially kind of in the long run interest of the organization.
All right, thank you, Florian. Okay. Yota says, thank you so much for this open lecture. It was great. Stay safe, everyone. You too. Thank you very much. All right. So I would say, Florian, thank you very much. And for all of you who have been listening to this very interesting open lecture, also thank you for your time and also for that interest. As we know, this is, of course, a subject that is going to become more and more complex. And in our digital business program, precisely, these are the kinds of topics that we discuss, that we tackle also with tools. So these algorithms and different programs that are used to understand all of these technologies are actually available and can be used and applied. So thank you very, very much, Florian. And of course, thank you to all the colleagues and to the students and to all our guests. And I wish you a great evening.
Thank you very much.
Kamina is asking for more information related to this. So that we plan sometime to get another open lecture. All right, we're gonna do that. Okay. All right, everybody. Have a great evening or a great afternoon, wherever you are, or even a great night, depending on where you're connecting from. Okay. So
cool.
Take care. Thank you, everybody.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.